Okay, today in class we learned how to solve systems of equations with inverse matrices, and then we also learned how to work with augmented matrices. So the first thing you're going to want to look at is we need to be able to write a system of equations as a matrix equation. To take a system, which is this, to write it as a matrix equation, we first take all of the coefficients from the variables, and notice that that sign will follow with the 12, and we create what's known as the coefficient matrix. The next matrix is what's known as the variable matrix, and then the last matrix is known as the constant matrix. Now, if I asked you to work backwards, and if I gave you a matrix equation and asked you to write a systems of equations, we would, because this is a multiplication that goes on right there, we would multiply each row by each column. So you would take 4 times x and then add a negative 12 times y, and that would equal this 7 over here, and that would equal that spot. Then you would do that again with the bottom. You would take this row by the column, so 1 times x would give you x, plus 6 times y would give you 6y equals 9. And if you notice, this system is exactly what we started with. And that's how the two are related, and that's how systems of equations can become that matrix equation. To solve a system, you're going to take the product of the inverse. So we're going to multiply the inverse of the coefficient matrix and the constant matrix, and this is the notation that says that we're going to take the inverse of matrix A and multiply it by matrix B, as long as the determinant cannot equal 0. The determinant cannot equal 0 because if the determinant is 0, then we cannot find an inverse. Remember that to find an inverse of a matrix, you have to take the inverse of the determinant. So if our determinant is 0 and we try to take the inverse of 0, this is what is known as undefined. So because the inverse is not, or does not exist, then you can, if it does not exist, then you cannot solve that system. And if that means we cannot solve it, that means the lines are parallel and do not intersect. So on this first example, what I'm going to ask you to do is to create a matrix equation. So to create a matrix equation, we take the coefficients, so negative 2, negative 5, 3, and 2. We multiply it by the variables. In this case, we have x and y. And this is equal to our constant matrix, negative 19 and 1. And then what we have to do from here is to find the inverse of matrix A, multiply it by matrix B. So if we take the inverse of A, the first thing you have to do is find the determinant. The determinant is found by multiplying this diagonal, the primary diagonal, so negative 2 times 2 is negative 4, and subtracting the product of the other diagonal. So 3 times negative 5 is negative 15, so this ends up becoming plus 15, and you get a determinant of 11. Once you have that, to find the inverse, we take the inverse of that determinant, so it becomes 1 over 11. And then if you remember, we switch places of the primary diagonal, so we get 2 and negative 2, and change the signs of the other diagonal. Once you have this matrix, you're going to multiply it by the constant matrix, which is negative 19 and 1. Now you can either distribute this 11 through to all, or sorry, 1/11 through to all 4 terms, or you can wait till the end. And I'm going to wait till the end so that I don't have to deal with fractions till the very end. So if you can remember, multiplying, we take the row by the column. So I'm going to take 2 times negative 19. And then I'm going to add 5 times 1. That's that first row. And then I take the negative 3, the bottom row, times the column. So negative 3 times negative 19 plus negative 2 times 1. And don't forget that I do have that scalar out front. So I'm going to change that a little. Make a little space for that 1 over 11. Okay. So from here, oh, there's an interruption. Sorry about that. Now you know I'm at school. Anyway, so to finish this, we're going to multiply 2 times negative 19, which is negative 38, and add 5 to get negative 33. And negative 3 times negative 19 is 57. We're going to add a negative 2 to get 55. And then the very last step is to multiply this scalar to both. Now see, aren't you glad I waited till the end so we didn't have to deal with that fraction till later? So that when we distribute the 1/11 through, we end up with a matrix that looks like this. And what that means is if we go back to our system right here, if we go back to that system, if we were to graph those two equations, they would intersect at negative 3, 5, and that's how I want to see your answer. I forgot what I was going to say. Anyway, what this tells you is that you have one solution. The two lines intersect at this point. Prior to this, I've taught you several different ways how to solve a system. If you remember, we started with graphing, then we went to substitution, we followed that with elimination. And then in this unit, I taught you how to solve using Cramer's rule. This is just another way to solve systems of equations. I'm going to show you, in class today, we actually did this in our calculators. I had my class store our coefficient matrix as A, and the constant matrix is B. And then once they were stored in our calculators, we took A, and then pressed the button that allows us to do an inverse, the inverse of A, and multiplied it by B. And it gave us the solution that actually did look like this. Negative 3, 5. So if you have a calculator at home, I would advise you to do it that route, or do it that way. If not, I guess you can do it by hand. Okay, for our second example, with the 3x3a, I'm going to ask that you, in fact, I think I say that on the next slide. Let me look. Yeah. It says to do this in your calculator and store the coefficient matrix as A and the constant matrix as B. So if I ask you to do it in your calculator, I've got to know what you put in your calculator. So I do want you to write the matrix equation first. So we take our matrix equation by writing the coefficients, 2, negative 1, 3, and 4, negative 3, negative 1, times our variable matrix, x, y, z, and this will equal your constant matrix, 3, negative 4, negative 18. And in your calculators, you'll store this as A, store this as B, and I showed you this on the previous slide. Once you've stored those, you're going to select A, the matrix A, press the button that allows you to do the inverse, and multiply it by B. And that should give you an answer. If it gives you a singular matrix error, I'll write that out. This means that the inverse does not exist because the determinant was 0. If the inverse does not exist, you can't multiply it by another by the constant matrix. So if it does not exist, then the two lines were parallel and they do not intersect. Alright, so when we stored this as A, took the inverse of it, multiplied it by B, it should give you a column that looks like this. What that means is that you have one solution located at -2, 3, 1. And we call this an ordered triple instead of an ordered pair. It means that if you were to graph all 3 lines, and I can't show you on this two-dimensional paper, but if you were to graph all 2 lines, they would intersect at one point. So I showed kids in class with pencils. I stacked 3 different pencils going different directions and showed them that 3-dimensionally we can have 3 lines that intersect at one point. And that's what that solution means. Okay, our next thing we're going to learn about is augmented matrices. An augmented matrix, it contains the coefficient matrix with an extra column containing the constant terms. So if I give you this system, and I did this intentionally because I wanted to show you what happens if we're missing a variable. If we're missing a variable, then we are going to replace that term with a 0. So an augmented matrix takes all of our coefficients and makes a matrix with it. So I'm going to show you right here. We have 1, -5, 1, 1, -5, 1, 3, 2, and the 0 represents that there was no z in that middle equation. And then the last one we have the coefficients. So then it also includes the constant matrix right here. And it makes it now, instead of a 3 by 3, we're going to use a 3 by 4. After that, after you have stored your matrix as an augmented matrix, we're going to use what's called reduced row echelon function. And what this does is it reduces the augmented matrix so that the solution to the system can be easily determined. So on example 2, we're going to use this. The first thing you're going to do, and this is what I'll ask you to do in your homework, is at least show me what matrix you created. Right now I'm taking all of the coefficients from the matrix, and then I'm going to add that last column, and I'm not really going to put those dashes there, but I wanted to show you that after that we list the constants. So what you're going to have to do is you're going to have to store this, and I'm going to go ahead and store it in my calculator as matrix A. And once that's stored, you're going to arrow over to math, and then you have to go up, arrow up or arrow down. I like to go down, or up because it's faster, till you get to a B option. And when you get to that B option, you'll see that it says RREF, and that's the reduced row echelon form. And once it's there, you can press enter. That should take you to your home screen, and then on your home screen it'll say RREF in parentheses, or then a parenthesis. Then you will go in and choose your matrix A and then press enter, and that's what it will look on your screen, and then I'll show you what it will look like once you press enter. So when you press enter, you're going to get something, or your matrix will look like this: 1, 0, 0, -2. And you'll get 0, 1, 0, 3, and 0, 0, 1, 1. And what this means, if you remember that this first one represents x, y, z, that's how you listed your coefficients. So this 1 represents, or the x represents our solution for x, or our value for x. So it becomes -2, 3, 1. So if you remember, that's the x, this is the y, and this is the z, and that's what each of them equals. See that mess that I just wrote over? See if I can write it in a different color. I'll try that again. This one represents x. This one represents y. This one represents z. So if you notice, it'll say x equals -2. And we can pick out that solution really quickly. Because this is a three-dimensional system, you have an ordered triple, and that's how you get those numbers. This column will give you the numbers. If you don't have, my one class said, hey, this looks like the identity matrix. So we said if you didn't have the identity matrix and followed by a column with values, then you would not be able to find this system, and it would be a no solution system where they do not intersect. Okay, good luck. A lot of this is on your calculator, so you might have to come in and see me to use your calculator.